Hello, welcome to Econometrics Melody. In this video, we will discuss about the OLS beta estimate. In fact, we will calculate or derive the value of OLS beta estimate. In our preceding video, we had seen that while calculating the derivative with respect to vector beta, if the numerator and denominator, they have same variable or the vector, if their order is same, then we take the transpose of the pre-multiplication or post-multiplication term. Similarly, if the numerator and denominator, the vector or the variable, they are in their transpose form, then we take the pre-multiplication and post-multiplication term in its original form without changing it. So it's, for example, here we are taking the derivative with respect to vector beta, and in the numerator and denominator they are same. That is why we take the transpose of this pre-multiplication term, that is matrix A. Similarly, in this example, again, if we compare the vectors A, the numerator and denominator, they are transposed to each other. That is why we take the pre-multiplication or post-multiplication term in its original form without any changes. We apply the same rule in order to calculate the derivative with respect to vector beta for this quadratic equation form, beta transpose AB. First of all, we concentrate on the beta on the left, that is beta transpose, and we compare it with the beta, the vector beta in the denominator, and they are in their transpose form. That is why we take the post-multiplication term in its original form, plus is we use the product rule. Now we compare with the beta at the extreme right and the beta at the denominator. They are same, their order is same. So in this case, we take the transpose of the pre-multiplication term, and if we operate it, this is our result. And in the similar fashion, if we take the derivative of beta transpose AB with respect to beta transpose, then we get this result. Now let us move to today's topic, that is we are going to derive the ordinary least square beta estimate. And we know that in matrix notation, the linear regression equation, this can be written as y is equal to xb plus e. So this is our first assumption, that is the dependent or independent variable can be expressed, their relationship can be expressed in linear form. More precisely, this assumption focuses on the linearity of the beta estimate, and from this relationship the error term, this is equal to y minus xb, and the sum of the square of the error can be written as y minus xb transpose y minus xb, and this is our optimization function, and we need to minimize the sum of the square of error, and we are in search of that beta estimate. Now let us operate it. So let us operate the transpose of this relationship. So we get it as y transpose minus beta transpose x transpose, because we know that AB transpose, this is equal to beta transpose A transpose, and y minus xb, and let us operate the simple multiplication. So we have y transpose y minus y transpose x beta minus beta transpose x transpose y minus plus beta transpose x transpose xb. So this is our optimization function, and the only unknown variable here is beta. So we are going to estimate this beta. Now let us take the derivative of this optimization function with respect to beta. So this is equal to, so here we don't have beta, this is equal to 0 minus, let us apply the rule that we have just mentioned in our introduction. So is the beta in the numerator and denominator, they are same, so we take the transpose of the pre-multiplication term minus, here if we compare it, the beta in the numerator and the denominator, they are transposed to each other, so we take the post-multiplication term in its original form plus, and here we are going to apply the product rule because we have two beta, one in the extreme left and one in the extreme right. First of all, let us consider the beta in the extreme left as our variable, and if we compare it with the beta in the denominator, they are transposed to each other. So when they are transposed to each other, we take the post multiplication term in its original form. Now let us consider the beta at the extreme right is our variable, and if we compare it with the denominator, so they are of the same order, so in that case we take the transpose of the pre-multiplication term. And if we solve it, this is equal to minus, here we are going to apply A B transpose, so this is equal to B transpose A transpose, so the transpose of the transpose is the variable itself or the vector itself. So we have x transpose y minus x transpose y plus x transpose x beta plus, and let us apply this rule to the transpose of the multiplication of the matrix. This follows the cyclic rule, so let us write here A, B and C. So in the clockwise direction beginning from A, we have A, B, C transpose. So this is equal to, so from the anti-clockwise direction beginning from C, so this is equal to C transpose B transpose A transpose. So if we apply this relationship, C is X, so it is X transpose, B is X transpose, so the transpose of it is simply X, and our A is B transpose, so the transpose of it is this. So this is equal to minus twice X transpose Y plus twice X transpose X beta, and this is our first order derivative, and we need to set it to 0 in order to minimize the sum of the square of the error. So we'll set the first order derivative to 0 and calculate its value later on. First of all, let us see whether this is the case of minimization or maximization. Now for that, let us take the second order derivative E transpose E and derivative of B. Now we need to take the derivative with respect to beta transpose because we have our beta, so let us take only two betas here, beta 0 and beta 1. And if we take beta and beta transpose, if we take the multiplication of this, then we can ensure the interactions of all the beta 0 and beta 1. If we operate it, we get beta 0 beta 0 beta 0 beta 1 beta 1 beta 0 and then beta 1 beta 1. So we get the interactions of all the possible betas, and it is equivalent to taking the partial derivatives with respect to these terms. So this is equal to, we don't have a beta here, so this is equal to 0 plus, and if we apply the rule once again, in the numerator we have beta and in the denominator we have a beta transpose. They are transpose of each other. That is why we take the pre-multiplication term in its original form. So this is equal to twice X transpose X, and the matrix X transpose X, it is positive definite, meaning thereby the eigenvalues of this matrix are positive. So this is equivalent to concluding that the second order derivative with respect to vector beta, it is positive. So when the second order derivative is positive, then the value attained after setting the first order derivative to 0, that minimizes the sum of the square of error. So now let us remember, this is our first order derivative. So this is the condition, minus twice X transpose plus twice X transpose X beta, this should be equal to 0. So this is the result of our first order derivative with respect to vector beta, and in order to optimize, we set the first order derivative to 0 and let us solve it. Twice X transpose X beta, this should be equal to twice X transpose Y, and then by the help of axiom of equality we have X transpose X beta, this is equal to X transpose Y, and then let us pre-multiply both the sides by inverse of X transpose X. And X transpose X inverse and X transpose X, they are inverse to each other, therefore the result is 1, and we are left with beta. This is our beta estimate. So this is finally equal to X transpose X inverse X transpose Y. So therefore beta estimate, so the OLS beta estimate, this is given by X transpose X inverse X transpose Y. And here comes our second assumption. So X must have full rank. So this assumption implies that any independent variable cannot be expressed as the linear combination of other independent variables. So this applies to each of the independent variables. So in other words, the full rank condition means the rank of matrix X, this should be equal to the number of its columns, and it must have the number of observations greater than or at least equal to the number of columns. So if we don't have full rank, then we cannot calculate the inverse of X transpose X, because in that case the determinant would be equal to 0 and we cannot calculate the inverse of X transpose X. So we had set the first order derivative to 0, and if we operate it, this is equal to, and we have our linear regression equation, this is equal to, so let us pre-multiply both sides by X transpose. So if we do that, then we get X transpose Y, this is equal to X transpose X beta plus X transpose E. So if we set the first order derivative to 0, then we get only this expression, which we can see on our extreme left. X transpose Y is equal to X transpose X beta. So setting first order derivative to 0, this implies that X transpose E, this should be equal to 0, or this ultimately automatically becomes 0 because we have set our first order derivative to 0 and we get this result. So setting the first order derivative to 0, it is equivalent to setting x transpose E equals to 0. In other words, we say that x and E, all the independent variables x and the error term E, they must be orthogonal. They are orthogonal. So whether we call it as assumption or this is the ultimate result, once we set the first order derivative to 0, the independent variable and the error terms, their interactions should yield 0 information. This should not provide any unique information. So this is the main message. And x transpose E equals to 0, it has another implication. So we know that x is the matrix of independent variables where the first column contains 1. This contains the column vector of 1. And let us represent other independent variables as x. This is our final x, or the matrix of independent variables. So this transpose E is equal to 0. And if we further operate it, this is equal to, so the transpose converts the row into column. So we get I transpose x transpose and E, this is equal to 0. And if we solve it, each of this would be equal to 0. I transpose E equal to 0, this means that the sum of the error term, this is equal to 0. So in OLS regression, the sum of the error is 0 due to we setting the first order derivative to 0. And the dot product of all the independent variables with the error term, this must be equal to 0. So we have seen that our OLS beta estimate, this is equal to x transpose x inverse x transpose y, and we have attained this by setting our first order derivative to 0. And once we set the first order derivative to 0, then the immediate consequences are x transpose E equals to 0 ultimately. And from this relationship, we get that the summation of E, this is also equal to 0. And the dot product of all the independent variables with the error term, this is also equal to 0. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.